Hello, this is Andy Pilc. It's day 13 of our astronomy unit, and in today's lesson, we're going to be talking about some rocket science. We'll talk about interplanetary travel using the Hohmann Transfer Orbit Method. So just to review orbits in general using this PhET simulator, we know that there are two things that are required of anything that's in orbit. One is the gravitational attraction between the celestial object and the object that's orbiting. So in this case, we would be talking about planet Earth and our sun. And the second component of an orbit is a forward velocity. So in order to leave Earth's orbit and travel to a planet that has an orbit outside of the Earth, scientists are essentially changing the velocity of a spacecraft. So they're kind of taking this and maybe increasing the speed a little bit and changing the angle. So that way the spaceship will leave the Earth's elliptical orbit and start traveling. So when it used to go out to here, it's going to travel in a more wide ellipse and meet up with the planet in an orbit that is further out than the Earth's orbit. So the video that you watched in today's lesson talks about meeting up with Mars, and the task in the PowerPoint asks you to devise a plan to use this transfer orbit method in a trip to Neptune. So a couple resources that are available to you. You have your ESRT that gives you all of the data about period of revolution and distance from the sun, which would come in handy. And just to give you a visual using open space. So here we have Earth, and we can know that the half of Earth that's going to be facing the sun is going to be experiencing day. And there's our sun, so let's focus on the sun. Oops. Just 1 second. So the terrestrial planets are going to be coming into view. And let's move the solar system at a rate of about 1 month per second. We're going to see Mercury, Venus, Earth, and Mars. So at this point in the orbit, this is about where we would see a spaceship leave Earth and use propulsion to leave Earth's orbit. And it's going to be traveling through space and meeting up with a ellipse that is further out and the planet Mars. And it would take some time for the spaceship to travel from Earth to Mars. So it winds up kind of meeting up about 200 days later, a little over 200 days later, on the Martian surface. So this is actually something that we've already done. We've landed rovers on Mars, and we've explored its surface, including the Curiosity rover just recently. And the tasks asked us to find a plan to land on Neptune, or at least join Neptune's orbit. So we're moving out to the Jovian planets. We see Jupiter, we see Saturn, we see Uranus, and then Neptune all the way out there in the blue. So we just kind of change our orientation a little bit. One last time. There's Earth's orbit. We can barely see it. And the task asks to find a plan to use the transfer method to travel from Earth out to the furthest planet's orbit. So good luck. Hopefully there's not too many lives depending on it, but just exercise in thinking and applying this method to traveling to different planets. So good luck. Okay, looking ahead for today, after you come up with your plan for traveling to Neptune, we have some practice with this series of Regents questions. So it says that the distances of Earth and Neptune from the Sun in astronomical units are shown beneath on the horizontal axis. And it gives us the distance of 1 astronomical unit there. The plotted line on this graph shows the relationship between a planet's distance from the Sun and the inferred temperature at its formation. The regions within the graph indicate the composition of the planets formed within these zones. So let's take a look at the questions that are related to this graph. It says, Neptune was mainly composed of which material at the time of its formation? Well, we can see Neptune right over here at its distance from the sun, and the composition shown in the middle. So we see frozen gases. Saturn is 9.5 AUs, so that would be right in between. These are counting by 1 each increment, so 9.5 right in between 9 and 10. See the approximate temperature, so we would just go up and intersect the y-axis to the left, and it would be just under the second increment line, which looks to be counting by 100 degrees Kelvin each increment. So a little less than 200 degrees Kelvin for temperature of Saturn. The relationship between a planet's distance from the sun and the temperature at which the planet formed. We would always use that sentence starter as a planet's distance from the sun blank. So here we're increasing distance. So we would say as the distance increases, what's happening to this line? Well, we see the temperature dropping. So as planet's distance from the sun increases, the temperature that the planet formed decreases. And what is Jupiter's distance from the sun in astronomical unit? We can look to the good old ESRT, answer that one. So here we see Jupiter's mean distance from the sun in a million kilometers is 778.4. So I'll plug that into my calculator. And the value for 1 AU is also given in millions of kilometers. So I can just divide this by 149.6. And there is my value for Jupiter's distance from the sun in astronomical units. To the nearest tenth, since that's a 0, we would just have 5.2 AUs. I hope you found this video helpful. I'll see you next time. Have a nice day.